Let's study about Torricelli's theorem. This theorem is about calculation of efflux velocity of a fluid flowing out through a hole in a container. In many applications we need to use it, and its analytical treatment is done on the basis of Bernoulli's theorem only. Say we consider a situation in which we are given with a cylindrical container and it is placed on ground, and say the whole container is filled with a liquid of density rho, and at the top it is open to atmosphere as atmospheric pressure is applied at the top, and say from the topmost level of liquid at a depth h below we make a hole in the container through which the liquid will start coming out. The velocity with which it comes out, we call it efflux velocity, and this efflux velocity can be calculated by using Bernoulli's theorem at 2 points. One is the point A at which the fluid is coming out, and other point we can take a point B which is inside, or we can also apply it at a point B which is at the top of the level. Now in this situation, if we use Bernoulli's theorem at just inside and outside points of hole, see what we'll be getting. Just outside we can take pressure to be P atmospheric, and if the flux velocity is V, the kinetic energy in the fluid flowing out can be taken as a half rho V square, and we can ignore gravitational potential energy as both of these points are at the same horizontal level. This must be the pressure at point B, which can be taken as P atmospheric plus H rho G, plus the kinetic energy here can be ignored. It can be taken as 0 as the area of cross section of container is considered to be very large compared to that of the hole, or we can simply write area of hole to be very less than the area of container. So we can ignore the velocity with which the fluid is flowing inside the container, and here P atmospheric also gets cancelled out, and here rho will also cancel out. Then the efflux velocity can be written as root 2 gh, and this equation we call Torricelli's equation of efflux velocity. And this equation we are going to use in different cases. Soon we are going to see a situation when the area of a hole is not very small. In that case, the efflux velocity will also depend on area of hole. But if we are given that area of hole is very small compared to the cross-sectional area of container, then efflux velocity is given by this expression, and it is only dependent on the height of free surface of liquid up to which it is filled above the point from where efflux is coming out.